Try combing your hair when it is dry, and then removing the comb over scattered bits of paper. You will find the pieces of paper get attracted to the comb. This is what happens when two objects are rubbed together. They become electrically charged. This is how the comb gets charged when you run it through your hair, and then attracts the pieces of paper. You may wonder where the charge comes from in the first place. Well, matter is made of atoms, and all atoms consist of charged particles. Are the charged particles arranged in any particular manner? Are the charged particles spread throughout the atom, or are they concentrated in one place? To answer these questions, let's go back in time. Dalton's atomic theory stated that an atom was indivisible and indestructible. However, in 1886, Goldstein came upon positively charged radiations in a gas discharge, which he termed canal rays. These radiations led to the discovery of the proton. The mass of a proton was about 2,000 times that of an electron, and it carried a positive charge. Around the year 1900, J.J. Thomson conducted experiments on the beams of particles inside a glass tube called a cathode ray tube. He found that the particles were attracted to the positive terminal of the tube. Thomson concluded that the particles must be negatively charged and called these electrons. An electron has a negligible mass and has a charge of -1. These discoveries made scientists believe that an atom was divisible and made up of electrons and protons. What they didn't know at that time was how the electrons and protons were arranged within an atom. They tried to understand this arrangement through various experiments. This lesson introduces you to different models related to the structure of an atom. By the end of this lesson, you will be able to explain why Dalton's atomic theory failed, list the postulates of Thomson's model, explain why Rutherford's model is relevant, explain the postulates of Bohr's model that build on Rutherford's model, and define shells. J.J. Thomson was the first to put forward a model to explain the structure of an atom. In his model, Thomson compared an atom to a Christmas pudding. The electrons were like the raisins in the pudding, and the pudding itself was like the positively charged particles. This can also be explained through the example of a watermelon. The positive charge in the atom is spread all over like the red, fleshy part of the watermelon, while the electrons are embedded into the atoms like the seeds of the watermelon. The oppositely charged particles are held together by electrical force of attraction. Thomson concluded that an atom consists of a positively charged sphere with electrons set within the sphere. An atom is electrically neutral as the positive and negative charges within it are equal. Thomson had said that the electrons were embedded in a sphere of positive charge. This turned out to be incorrect. Thomson had explained that the positive charge spread through the atom held the negatively charged electrons due to electrical forces. This assumption failed to explain many experimental observations made by other scientists. Thomson's student, Ernest Rutherford, conducted an experiment using gold foil which disproved Thomson's model. For his experiment, Rutherford used a gold foil which was about 1,000 atoms thick. he made a narrow beam of alpha particles fall on the gold foil. Alpha particles are doubly charged helium ions and have a mass of 4 atomic mass units. The result of the experiment was unexpected, as it did not follow the structure of an atom as known scientists at that time. Rutherford found that most of the alpha particles passed straight through the gold foil without getting deflected. A small fraction of the alpha particles were deflected through small angles. A few alpha particles bounced back. Based on these observations, Rutherford concluded that most of the space inside an atom is empty, as most of the alpha particles pass through the foil without getting deflected. Very few particles were deflected from their path. This deflection was caused by the repulsive force of the positive charge in the atom. The positive charge was concentrated in a small area within the atom and was not spread throughout the atom as Thomson had proposed. Based on his observations, Rutherford proposed the nuclear model of an atom. The positive charge is concentrated in the center of the atom, which is called the nucleus. The electrons revolve around the nucleus in circular paths called orbits. The nucleus is much smaller in size than the atom. According to Rutherford's model, the electrons, while moving in their orbits, would give up energy. This would make them slow down, gradually move towards the nucleus, follow a spiral path, and then fall into the nucleus. Ultimately, the atom would collapse. In reality, however, an atom is stable. Therefore, this particular assumption made by Rutherford was inaccurate. Keeping the shortcomings of the Rutherford model in mind, Niels Bohr formed his postulates about the structure of an atom. Electrons have discrete orbits called shells inside an atom. Electrons revolve in their orbits without radiating energy. Within a particular orbit, the energy of an electron is constant. This is why orbits are called stationary orbits or stationary shells. Orbits or shells are also known as energy levels. Shells are represented by the letters K, L, M, N, or the numbers 1, 2, 3, 4, and so on, depending on the number of shells in the atom. However, Bohr's model did not apply to elements like helium and lithium. The model was also unable to explain the structure of chemical bonds. Despite the limitations of their atomic models, the work of Thomson, Rutherford, and Bohr is considered path-breaking. All three scientists received Nobel Prizes for their theories. Therefore, these three atomic models are the foundation for our present-day understanding of the structure of an atom.
I wonder, what's the maximum I can score in this game?
You can't score more than the total of the ball points, as the number of balls in this game is fixed. Similarly, based on the study made by different scientists on an atom, concluded that any atom is made of fixed number of charged particles called protons and electrons. This lesson is about the internal structure of an atom. At the end of this lesson, you will be able to define atomic number, define subshells, determine the electronic configuration of an element given its atomic number, determine the valency of an element given its electronic configuration, explain the concept of a neutron based on Chadwick's work, define atomic mass, define isotopes and isobars, and list the applications for isotopes. Scientists propose that an atom is made of two kinds of particles. The positively charged particles are protons, and the negatively charged particles are electrons. Every atom of an element has a fixed number of protons in its nucleus. This fixed number of protons is referred to as an atomic number. This number is constant for an element. It is represented by an alphabet Z. Moreover, the number of electrons in an atom of an element is also equal to the atomic number of the element. For example, if the atomic number of an element is 12, then its atom contains 12 protons and 12 electrons. In an atom, electrons are not randomly placed around the nucleus, but they are placed in fixed energy levels called shells, as per Bohr's atomic model. These shells are named K, L, M, N. The arrangement of electrons in these shells is known as electronic configuration. For example, carbon has 6 electrons. Its electronic configuration is 2, 4. 2 electrons are placed in K shell and 4 electrons in L shell. In order to write down the electronic configuration of an element, one should have knowledge about the number of electrons in one atom of the element and the maximum number of electrons that can be accommodated in different shells of the atom. The maximum number of electrons that can be accommodated in any energy level of the atom is given by a formula 2n to the power of 2, where n is the number of that energy level. For example, the number of electrons present in the first energy level, n equals 1. According to the formula, 2 multiplied by 1 to the power of 2 equals 2. So, the maximum number of electrons present in the first energy level is 2. According to Bohr's model of an atom, the first energy level K can have 2 electrons. The maximum number of electrons which can be accommodated in shell L is 2 multiplied by 2 to the power of 2 equal to 8. Similarly, for M and N shells, the maximum number of electrons that can be accommodated are 2 multiplied by 3 to the power of 2 equals 18 and 2 multiplied by 4 to the power of 2 equals to 32 respectively. During the arrangement of electrons in the shells, the outermost shell of an atom cannot accommodate more than 8 electrons, even if it has the capacity to accommodate more electrons. Generally, the outermost shell of an atom can have a maximum of 8 electrons only, even though it has the capacity to accommodate 18 electrons. This is due to the fact that having 8 electrons in the outermost shell makes an atom stable. There is an exception. If the outermost shell is the first shell or K shell, the shell can hold only 2 electrons. For example, helium has only 1 shell in its atom. Electrons in an atom do not occupy a new shell unless all the inner shells are completely filled. The filling of electrons in an atom is a stepwise approach. First, the electrons are filled in K shell, then in L shell, M shell, N shell, and so on. There are few exceptions to this rule, which are applicable to elements with an atomic number more than 18. After a series of experiments and a detailed study by scientists like Louis de Broglie, Schrödinger, Sommerfeld, etc., it was proved that shells have energy levels within them and are subshells. These subshells are S, P, D, and F. Electrons are distributed in these subshells. Every subshell can accommodate a fixed number of electrons. The S subshell can hold a maximum of 2 electrons, a maximum of 6 electrons in the P subshell, 10 electrons in D, and 14 electrons in F. Electrons are distributed in their respective shells and subshells. The first energy level, K, can have one subshell which can accommodate 2 electrons. The next shell is the L shell, which contains S and P subshells, where the S subshell accommodates 2 and P shell 6 electrons. M is the third shell and have S, P, and D subshells, which accommodate 2, 6, and 10 electrons respectively. Next is the N shell with S, P, D, and F subshells accommodating 2, 6, 10, and 14 electrons respectively. Let's observe the distribution of electrons in the given 20 elements. Electrons in an atom are arranged in definite shells. The electrons which are present in the outermost shell of an atom are referred as valence electrons. From the octet rule, an outermost shell of an atom can accommodate 8 electrons. It was observed and concluded that an atom with completely filled subshells are stable and do not react easily. In other words, it means that the combining capacities are 0 or nil. The outermost shell of inert gas elements whose subshells are completely filled are stable. For example, helium and neon, where helium has 2 electrons in its outermost shell and all other inert gas elements have 8 electrons. The combining capacity of the atom to form molecules either with the same or different elements is defined as valency. For example, elements like hydrogen, lithium, and sodium atoms contain 1 electron in the outermost shell. Therefore, they can lose 1 electron. So their valency is 1. If atom contains less than 4 electrons in its outermost shell, the valency of an atom is equal to the number of electrons present in the valence shell. For example, aluminium has 3 electrons in its outermost shell, so the valency of aluminium is 3. On the other hand, if the outer shell has more than 4 electrons, the valency is 8 minus the number of electrons in the outer shell. For example, chlorine atom has 7 electrons in the outermost shell. Here, in this case, it is easier for chlorine to gain 1 electron instead of losing 7 electrons. Hence, its valency is determined by subtracting 7 electrons from the octet, which gives the valency of 1 for chlorine. Let's examine the element helium. It was found that helium has 2 protons and 2 electrons. However, its mass was found to be 4 times that of hydrogen. Similarly, the weights of some other elements were also found to be double or more than double the weight. For example, the number of protons in chlorine is 17, but its mass was found to be 35. Similarly, number of protons in mercury is 80, but its mass was found to be 200. This problem was solved when James Chadwick discovered another particle, neutron. Neutron is a neutral particle with a mass equal to that of a proton and is present in the nucleus along with the proton. An interesting aspect came into picture after the discovery of a neutron by Chadwick. Till then, only the atomic number of an element was in existence, which referred to the number of protons present in the nucleus of an atom. The total mass of the protons and neutrons inside the nucleus was regarded as the atomic mass of an element. Therefore, atomic mass can be defined as the total number of protons and neutrons present in one atom of an element. For example, one atom of sodium element contains 11 protons and 12 neutrons. So, the atomic mass number of sodium is 11 plus 12 equals 23. The mass number is denoted by an alphabet A. Now, let's try to derive a relationship between mass number and atomic number. Mass number equals the number of protons plus number of neutrons. Since the number of protons in an atom is equal to the atomic number of the element, the above relation can be rewritten as mass number equals atomic number plus the number of neutrons. The atomic number and mass number can be indicated on the symbol of an element. The atomic number is written as subscript on the lower left side of the symbol, whereas the mass number has a superscript on the upper left side of the symbol. Normally a carbon atom has 6 protons and 6 neutrons, but some unstable carbon atoms were found. These carbon atoms had 6 electrons, but the nucleus was similar to that of a nitrogen atom and it had a mass of 14. Soddy discovered that certain elements had a heavier mass. Their atomic number and chemical behavior was same, but their mass was slightly higher. The higher mass is due to the presence of extra neutrons. Soddy called the elements with same atomic number and different mass number as isotopes, Greek meaning same place. Thus, isotopes are atoms of the same element with the same atomic number but a different atomic mass. The valency of isotopes is the same. Isotopes of the same element differ in their physical properties. For example, 12C6 and 14C6 are isotopes of carbon. 1H1 protium, 2H1 deuterium, 3H1 tritium are isotopes of hydrogen. 35Cl17 and 37Cl17 are isotopes of chlorine. The chemical properties of all the isotopes of an element are the same. This is due to the presence of same number of electrons. Rarely some isotopes have special properties which were found to be useful in various fields. For example, an isotope of uranium is used as fuel in a nuclear reactor. An isotope of cobalt is used in the treatment of cancer. For treating goiter, an isotope of iodine is used. In some cases, it is also possible that the atoms of different elements have different atomic numbers, may have the same mass number. Such atoms are called as isobars. For example, argon with atomic number 18 and calcium with atomic number 20. The number of electrons in these atoms are different, but the mass number of both these elements is 40.